Hello, everyone, and thank you so much for coming. Our group name is BLAST, and we've studied balloon at low altitude studying temperature. Now let's meet the team.
Hi, my name is Aanchal and I'm from Austin, Texas.
My name is Fiora Beratahani, and I'm from San Jose, California.
My name is Hayden Thompson, and I'm from Oakland, California.
My name is Jamin, and I'm from San Jose, California.
Hello, my name is Kathleen Cravens, and I'm from Lakewood Ranch, Florida.
And I am Seth Cohen, and I'm from Los Angeles, California. Throughout the course of this project, we had the privilege to work with our mentors, Dr. Brandon Jones, an assistant professor in the Aerospace Engineering Department at UT Austin, and Rachael Gold, a PhD student studying orbital mechanics at UT Austin.
Now we will walk you through the significance of our work. In this process, we really wanted to prioritize engineering exploration, and we were able to encapsulate the essence of electrical, mechanical, and aerospace engineering all into one project. And through the use of data collection, we wanted to understand more about physics and theoretical analysis behind climate science. For our background, I will take you through some of our project structure and goals. So for our mission level objectives, we wanted to prioritize both understanding and application of new scientific concepts. So first, we sought to understand the variations in the temperature based on altitude. And we did that with the goal of verifying theoretical variations in temperature based on the Earth atmospheric model.
Now let's get to the approach. We followed the NASA systems engineering process for the design of our project. NASA's online modules helped to educate us on the process. Then we had to brainstorm risks and ways to mitigate them. We made a risk chart as shown here to compare the likelihood and severity. For example, in order to mitigate the risk of electrostatic discharge, which could shock and damage our sensitive electronic components, we wore ESD bracelets while working with the parts.
Our system consists of the balloon and the banana. The balloon refers to the weather balloon itself and the tether between the balloon and the banana. The banana is the structure and everything within it.
We split up our system into 7 subsystems and came up with requirements for each subsystem.
As part of the NASA systems engineering process, we filled out a requirement verification matrix. This diagram shows a hierarchy of requirements. The mission objectives instruct the system requirements, which inform the subsystem requirements. We've included an example regarding temperature collection.
For the command and data handling subsystem, I researched potential microcontrollers and I weighed the benefits and downfalls of the different options, ensuring that they fit the requirements we stated earlier. I ended up deciding on the Adafruit Feather M0 Adalogger because of its ability to store data on a microSD card without an outside extension, as well as its capability to use I2C wiring, among others. After selecting a microcontroller, I wrote code to test it and its compatibility with the sensors. I tested its ability to store data on the microSD card and to read measurements from the sensors, and I also tested how everything worked when it was integrated together. In addition, I wrote the program for the experiment mode, which collected data during the launch of our balloon. The photo on the left is a test that we were conducting using a breadboard before we were able to solder everything. The photo in the center is of the data that was collected during the freezer test, and the photo on the right is an Arduino program written to test the ability of the microcontroller to store measurements on the microSD card.
So I was in charge of payload, and I researched the temperature and altitude sensors that we would use for data collection. Based on measurement accuracy and microcontroller compatibility, we decided on the sensors up on the screen. The diagram on the right is the wiring layout, and the bottom left photos show the sensors within the structure. We decided not to use a breadboard in our final product in order to minimize the banana size and weight.
I was in charge of the thermal protection system and the environmental protection system, both of which require a lot of risk analysis. And I sought to protect both the interior and exterior of our system. Something I focused on a lot was actually the wind's effect on altitude. So if you place your attention to the image on the right, the red circle, the larger red circle, represents our balloon, and the blue squiggly lines represents wind. And the force diagram right next to that essentially depicts what would happen if wind acts upon our system, which in this case tilts the balloon to the right and knocks it off its original trajectory of pointing straight up. So since wind would be acting upon the balloon in our launch, I constructed a Python program to account for this. So at the bottom of the screen, you'll see an image where this Python program takes in user inputs. And for the estimate, I used 2.7 meters per second of wind, which is roughly around 6 miles per hour of wind. And we wanted to reach 1,000 feet with our system. So the system is telling me I would need around 1,107 foot of tether in order to reach that desired altitude of 1,000 feet. So I made an official recommendation to extend our tether in order to reach this desired altitude and add up to 10% to our original tether length.
Now for the MGSE and EGSE, which stands for the Mechanical and Electrical Ground Support Equipment. One thing I was in charge of was the ground test procedures and code. And based on the requirements and necessary tests for all subsystems, I designed integrated test procedures and wrote code to test the sensors and the expected function of the hardware in the banana. I was also in charge of the data analysis and the ground station computer. So I wrote Python code in Jupyter notebooks to calibrate the sensors and analyze gathered sensor data. Here's a sample plot from a temperature sensor test while we were at the launch site. I also operated the ground station computer, which was for quick data analysis at the launch site.
For my subsystem, which was electrical, I had to calculate the power budget by researching and selecting sensors with CDH and payload. After selection, I had to calculate the total amount of volts, amps, and watts that were needed to supply the system. From there, I selected a battery that would meet this requirement. Before integrating the battery, we had to conduct tests with a multimeter to ensure that there was resistance in the battery. After testing the battery and integrating the circuit, we tested the connections between the sensors and the microcontroller to make sure the correct connections showed resistance.
Regarding the structure, I needed to design a case that would store all of the necessary components. I used the 3D modeling software Aanchal to create a structure that was eventually 3D printed. Included above are some photos of the design as well as the final product. For our control and guidance of the balloon, I had to first determine the right amount of helium required to produce positive lift. I used the number 100 grams as my starting value for the lift required. I created a calculator which would take it in the different weights of the equipment that we used and determine how much helium was necessary. After that, I had to effectively secure the tether to the ground and determine a method of increasing altitude in 50-foot increments. In the middle photo of the slide, you can see the calculator that I used to determine the helium requirement. And in the photo on the right, you can see me securing the tether onto the ground.
We performed a number of additional tests and procedures to try to ensure as successful of a launch as possible. We tested all of the systems integrated together, as well as a few calibration tests, such as a freezer test and a drop test. Through these tests, we verified that our sensors and our system all worked correctly, and that we accounted for any error or variation that we would be seeing in the data on launch day. We also tested our parachute to confirm that it would work correctly for the launch.
One of the integrated tests that we performed was a freezer test. In this test, we tested this temperature sensor by putting it in a freezer. Since the temperature took some time to go down, a least squares exponential fit of the error of the temperature measurement compared to the freezer's display temperature, which was -15 degrees Celsius, gave us a good calibration result. We can see that the sensor has a small bias from the true value, since the error was exponentially approaching 0. And the sensor precision matches the standard error of the residuals of the measurements, which means that through testing, we have confirmed the precision of the sensor. Another integrated test that we performed was a drop test. In the drop test, we released the banana from the 4th floor of the CSR to simulate using a balloon to move the banana through different altitudes. We calculated the standard deviation of the temperature at each measurement stop to compare with the sensor precision.
Now let's see what happened. Before the launch, we had to calculate the helium, do a ground test of the payload sensors, secure the banana, and deploy the balloon. During the launch, we went to an open field at the J.J. Pickle Research Campus. Here on the left, we can see Seth attaching the banana to the balloon to prepare for the launch. In the middle, I am carefully releasing the tether at 50-foot intervals in order to ensure that the sensors have time to collect the data. On the right, we can see our balloon flying high in the sky.
Unfortunately, after collecting the balloon and checking the data, we found that we had only collected 40 seconds of data instead of the 90 minutes of data that should have been collected from the launch. After some analysis, it was evident that this data was taken at the beginning of the launch, after unplugging the USB cable and before we let go of the balloon. We now needed to determine the exact cause of this data loss.
Given the contrast between our previously successful test and our lack of data collection during the launch, we have to ask the question of what went wrong. On this slide are 4 key factors that we believe led to the lack of data collection. First was wind. The estimated wind was around 6 miles per hour prior to the launch. However, during the launch, the wind speed was around 5 meters per second or 11 miles per hour, nearly double of what was previously estimated. We believe that this wind may have moved our electronics, including the micro SD card, which held our data. Additionally, during the launch, the temperature was around 105 degrees Fahrenheit, so our system could have possibly overheated during this time. Additionally, the battery may have discharged, or we might have faced code compiling or uploading issues.
So what could we have done differently? Well, if we were to run this experiment again, ensuring that we did collect data, here are some things we would do differently. We would launch the balloon earlier in the morning because that would reduce wind and lower the temperature, reducing the possibility of failure due to either of those factors. In addition, we might downlink data to the ground station in order to check data was actually being collected or to check system health and function. Another idea of something we might change, were we to run this experiment again, is to go up to a lower altitude, say 200 feet, then come straight back down to ensure data was being collected. The last thing we could do was to add an LED indicator to flash when data is being collected. This would give us a visual cue to make sure that data collection was taking place.
So this section is about our reflection on our project and on the entire SEAS experience. Beside the lack of data collected from our flight, we faced a nationwide helium shortage at the start of our project, so we weren't even sure if we were going to launch. Some of our alternative ideas were releasing the banana off the building or using a drone. Luckily, however, we were eventually able to secure helium. Additionally, we also only had one chance to print our structure, so we had to work around a few problems. One of which was that there was no space to connect the components using jumper wires. So we had to solder wires directly to the microcontroller and sensors. Also, we had to remove the lid of the banana at the launch because the temperature sensor was providing inaccurate measurements.
Now that our project is complete, it is time to reflect on our SEAS experience. I'm Aanchal, and I'm an aspiring computer science and computer engineering major, and this program has helped me learn more about the different potential STEM fields, as well as to delve deeper and improve my knowledge about certain things within those fields, such as working with electronics. My favorite part of this internship was being able to physically create something and seeing our design progress through the phases of the NASA systems engineering process. I really enjoyed being able to collect real-time data during our tests and analyze and improve upon it.
I'm Fiora. SEAS solidified my decision to pursue either mechanical or electrical engineering because I really enjoyed working on sensor integration through a hands-on project. I also liked all the team building activities that were provided by SEAS that helped me develop a close bond with my teammates during this short period of time.
I'm Hayden, an aspiring computer science and mechanical engineering major, 2 areas that I got to explore further during this internship. 2 of my favorite memories of the SEAS internship were Dr. Hun Mandel's talk, including when I got to speak with him afterwards about the privatization of space travel. I also thoroughly enjoyed our tour of UT Invention Works, where they had a plethora of 3D printers, laser cutters, and student projects on display.
I'm Jamin, and I aspire to be an electrical engineer major in the future. Going through the entire engineering process from start to finish has expanded my knowledge and experience in engineering and programming. One of my highlights from SEAS was learning new Python libraries for statistics. which will be useful for future work in engineering and data analysis. I also enjoyed Dr. Carl Gebhardt's talk on black holes and dark energy and his work on head decks.
Hello, I'm Kathleen, and I'm an aspiring mechanical and aerospace engineering major. And SEAS has helped me to dive further into the engineering process and deepen my interest in aerospace. My favorite part of this experience was talking to a former SEAS intern at the Johnson Space Center. It was so fascinating to hear about his experience as an intern at Johnson, and I hope to be able to follow a similar path in the future.
And I am Seth, an aspiring mechanical engineering major. And I think that SEAS has provided me with the opportunity to use the mechanical engineering process, incorporate scientific research, and develop a real-life project to accomplish a given task. My highlight of the entire program was our tour at the Johnson Space Center, where I was able to view cutting-edge research and meet with scientists who are doing exactly what I want to do in the future. These are the sources that we used, and we would like to say thank you so much for listening. We want to give a very special thank you to our mentors, Dr. Brandon Jones and Rachael Gold, as well as NASA, the Texas Space Grant Consortium, and the Center for Space Research. Thank you again.